Hi guys, since today is my almost Y100th video, I decided to bring the phase shift full bridge. So no more wasting time, and let's immediately do that. So now I will explain everything to you. So this is a classical full bridge with the phases and the inductor, the transformer, sorry. Okay, and these are the four MOSFETs A or 1, B, C, and D. So in a classical phase, in the classic full bridge, the PWM of A is equal to D, and it is a normal square wave, like this. And B and C are equal, but they are phase shifted of 100 degrees. 180 degrees, like this. So they are basically complementary. Of course, there is the dead time, and the primary voltage of the transformer becomes like this. When the PWM A is equal to is on, it means that you have V in here. And then it goes, and then in the full bridge, it goes to minus V in, but there is, of course, the dead time, and so it goes like this. Yes, my drawing is so horrible, but it is like this, okay? So let's see what happens now in the phase shift full bridge. So QA and QB are the two identical PWM, which are of course complementary to one another, like always. Okay, but QC instead of being exactly the same as B, like it should, okay, like it was here, you have C phase shifted of an interval which we call alpha. This interval here is will make some changes in the primary voltage of the transformer and also in the output voltage. When these two are in phase like this, there is a short circuit in the primary voltage, in the primary transformer voltage. Let's see why. You have this point here and this point here, okay? Sorry, not a short circuit. There is my mistake. We call this voltage here VP, and VP is equal to VA minus V VB. This is A and this is B. Okay, VA and VB. Now, when QB is on and QC are on, both of these are on, C is closed and B is closed. And then D and A are open. So if that happens, it means that VA QB is on, yes, so VA is equal to 0, and VC is closed, so it is connected to V in, namely that VP in this interval is minus V in. Let's see what happens when there is only QB on and QC off. If QB is on, is closed, then you have VA shorted to ground, but VB, this point here, is not on because you have QD is closed to ground as well, and so you have this point here to which is 0. So 0 minus V in, and the cycle repeats to the contrary to the contrary when you have V in. And so the primary transformer current, of course, will be that when you have when here you have V in, the inductor charges, and so you have the interval in which is rising, and then it basically it's almost the same as almost, but not so precisely, but almost the same as any charging and discharging transformer. Okay, so now I want to show you this script that I made. This script here is basically how to you insert the V in, P in, P out, and everything, and basically the script returns you all the parameters that you need to design for the full bridge. Okay. Of course, there is no I did not insert the parameter alpha because it was quite difficult. But anyway, you just insert the V in, V out, and the script will give you everything that you need to know, included also the primary and second inductance to make the transformer on LTSPice. So now I open LTSPice, and just to test the script, I opened the LTSPice, which is already done. So the primary inductance is 0.81 and the second inductance is 1 millihenry. This is the ratio that will convert you to from 400 volts to 14 volts. And then you have 2 microhenry and 100 microhenry according to the script. I put a little bit more capacitance because with the capacitor is better to have a bit better abundance. Let's reduce it a little bit, but so let's run the script. Now let's analyze. This is a full bridge, okay? Not yet a phase shift full bridge. Sorry, this is a mistake. Let's cancel D. Let's cancel 1 minus D. This is just D, okay? And there we go. So let's analyze first this. As you can see, this is M1, and it's the same of this. And then you have this one, which is complementary. There is the dead time of 100 watt a second. And now the primary voltage, which is of course this. And here there is the dead time. And then you have the secondary voltage here, which is between minus 14 and plus 14. And then you have, of course, the output voltage, which is okay, it's not 14 volt, just because we have a very high current flowing. We have more than 100 amps, so it is natural. If I reduce the load, so let's put 100, we should have 14 volts. Ah, we still are in the transient. Let me check just the okay. Because I put it here. So let me put 1 milli and 1.02 milli. Okay, let me put 0 and 1 milli. Let me put a higher load. Okay. So we have the drop of the diodes. Of course, we have it. And but by the way, we can just stop the simulation at 500 and start to 480 micro. Yeah, it's good. Yeah, it's good enough. So as you can see, is so the script is working fine because he calculated everything. Okay, and we have the secondary current max because I put the maximum load in the script, but yeah, I don't care. But by the way, the transformer is good because we have minus 14 plus 14 as we expected. And now we have to implement the phase shift full bridge on LTSPice. we expect not only the parameters from the voltage to change, but also the output voltage VO as well, because the output voltage will be regulated by this interval alpha. Okay, this interval alpha here. It is not proportional, so you don't expect to have VO equal to NS over NP times V in times D times alpha. No, not like this, but you have something like sinus of alpha over alpha. Yes, this is an approximation, but by the way, it is not linear. Okay, it is not linear. So how we can do this? QA and QB are the same. So let's check on LTSPice. So M1 and M3. Let's cancel all of this. We don't need that. Even this, we don't need it. So these two. So these two remains as they are. Remains as they are. And these two are correct. Now we must make QC a little bit more shifted, plus alpha of an angle called plus alpha, and here of the same angle but minus alpha. You see, because here in the graph QC has a phase shift of 2 alpha, but this guy QD has minus 2 alpha with respect to A. So we have to make the things very clear and symmetrical. By the way, I took this by an application note of Texas Instrument, which I will show you later. Okay, phase shift, full bridge, DC power conversion, and these are the waveform that he showed me. So we have to make this. To do this, I suggest to use the waveform M4, the waveform of M4, which is VG1B. We put a delay of a parameter called alpha over F switch over Fs. In this way, we are defining a parametrical delay based on the switching frequency. In this way, it will be easier to regulate this translation. So let me run the simulation just for now. Probably it's not working. No, it's not working. It's not working anymore because it's not a full bridge anymore, because I'm not doing the things correctly. So I needed to simulate just the first 20 milliseconds, and that's it. Okay, 20 milliseconds should be enough. So this is this is the B, and this is M1. Okay, as you can see, I translated a little bit of this interval here, alpha, which is 0.2, exactly as the paper reported. So so D is translated, is shifted of an angle called alpha. Let us make 0.3, for instance. Okay, so as you can see, I shifted even more with respect to the waveform, the waveform that we need. Okay, now it is more similar to the paper, I guess. And we have to make the same for the other guy. Okay, we have to make the same for the other PWM. So I translated this M1, M4. Okay, now we have to take M2. Oh, sorry. Sorry. Wrong waveform. Okay, now we have to take M2. The C, okay, the C is A and B remains the same. Okay, A and B remains, so you have to take this waveform here, VG2, so this waveform here, and translate it and translate with a parameter called alpha over fs. Should be like that. Should be like that. I hope so. Or something wrong is happening. I don't. Okay. So let me check again v4 and this m3. Okay. So let us put 4 plots so it is more clear. This is the first. So we have the same plots, QA. Then we have QB. Ah, so I made it wrong. No. It's correct. VG2B is this. And as you can see, we have A and B. Then we have QC, which is my M3, which is my, sorry, M2, which is VGA-B. This is the third, and QD is the last. Let us see if they are the same. No, because V2AB, QD is correct. It is easy, but is just take a flame shooter and put it on the paint. So let's see if they are the same. Okay, this is QA and QB. And for now, they are the same, as you can see. Now, QD, it has this interval here. So it's okay. QC is wrong because it has to be translated from the other side. I think. Because QC, yes, QC is wrong. Because you see that QC has to be delayed from the other part. So it is my mistake. Maybe we should put a plus. B2A and B. We should put not minus, but a plus here. Let's put a plus. Okay. Okay, now it seems more. Now it seems now the waveform seems more reliable with respect to the paper. With respect to the paper here. Let's confront them again. And QC, as you can see, if you see QC and QD never overlaps themselves. So when this is on, this is off, and now it is respected even in my simulation. So if this is on, this is off. And you have the phase shift in the red and this one. So I think that we are good to go. The waveform are now correct. Trust me, guys, that this is not easy. Okay, this is not easy. Really, this is not easy. I hope that LTSPice does not crash, but the waveform should be easy. Should be correct. The simulation is very slow, but it should be correct. And I hope that nothing wrong happens. Yes, the simulation is horrendously slow, and I'm afraid that it's about to crash. I'm afraid so. The simulation may be like this because we are creating short circuits. So if I see the primary voltage. Okay, the primary voltage is correct because when I create the short circuit is to 0, as you can see. So yes, it is correct. Spice is slow because we are creating short circuits at each interval. Probably that's the reason why. And maybe if I put a resistor here, I will not create a short circuit anymore. And but yes, the simulation it seems good to me. Seems good. Yes, aside from the current that is debatable, but the primary voltage is indeed correct. The inductor is charging, I guess. Yeah, the inductor is charging, so. Now, as you can see, the output voltage is not anymore, as you can, whoa. As you can see, maybe I can stop the simulation. Okay, let's stop it there. As you can see, the output voltage is not 14 volts anymore. That's why that's the reason why is that because the parameter alpha influences the output voltage. Okay, so if now I decrease alpha to 0.2, the output voltage will change again. Again, I do hope that this is not crash anymore. You see that now you see that now that I put a parameter alpha more closer to 0, the output voltage has increased with respect to the previous simulation. Yeah, we can stop the simulation here because it's pretty clear where it is going. So what does it mean to reduce alpha? It means that you can control the interval in which basically you have the you can control the interval in which basically the transformer is not shorted to 0. And having that, meaning having less interval in which the transformer is not 0, meaning that more energy is going to be delivered to the secondary output. Okay, so if I put if we try to reduce even more that interval over there, you see that the simulation is even more smoother because basically there is no more the interval in which the transformer is 0 has been reduced even more, and so as you can see I have a greater output voltage. If instead alpha is 1.15, I am increasing the interval in which transformer is 0, so less energy is delivered to the output. So guys, I think that we can stop the simulation here. Now it is slower, the simulation is lower because the interval has increased. Okay. I expect to see peaks of short here. Yes, of course there are. Of course there are. Of course. Of course there are. Okay. So we can, so for me, this is the simulation of a phase shift for bridge. I hope that you did enjoy it. And Happy New Year, guys. And see you in the next video.